Now we're going to learn how to analyze simple machines. Machines are items that can have motion, although we will analyze them in a static fashion. In addition to that, machines can alter forces or alter the effects of forces in advantageous ways. For example, I have this set of pliers here, and these pliers can move, and it has a pin joint here that allows it to move. In addition, we apply a force to this side here, and it multiplies that force on the clamping jaws on this side. So let's analyze this system. So I'll move over to the desktop view, and I've drawn a simplified view of the pliers here. And I've labeled this L1. This is the distance from the force to the pin. And we have L2 here, which is the distance from the pin to the clamp, or the part that we're clamping. And then we also have theta here, which is the angle offset. Okay, so how do we analyze this? Well, first off, it's a good idea to break this into pieces. All right, so break it into two pieces. So we'll take off this this jaw, and we'll take off this jaw and analyze those separately. All right, so I have that already laid out. Okay. So I've taken this off, and we also want to analyze the part that we're clamping. So the part that we're clamping is this round cylinder, and it's going to be clamped in both directions here. By some force. Let's just call that FC here. On both sides, clamped by FC. Okay. Since this is an internal force, so as you see on the pliers, this FC force does not appear anywhere. It's an internal force. So if we start taking parts, breaking parts apart, we are exposing internal forces, and internal forces, when we add everything back together, must cancel each other out. So on the jaw here, we have to draw the clamping force in the opposite direction. So we have FC in the opposite direction. So if we were to add these two together, these clamping forces would cancel each other out. That makes them an internal force. Okay? In addition to that, we have at the pin right here, we will have a force in the Y direction, which we'll call AY, and a force in the X direction, which we'll call AX. Okay, so now we've taken the pieces apart. We've made sure that the internal forces cancel here with the clamping force. And now we can use our equations of equilibrium to solve this problem. Okay, so the first one, why don't we just take the moments around A and set those equal to 0? And we'll call counterclockwise positive. And we'll just use our conventional coordinate system here. So we have this force F, and this force F around A is going to create a counterclockwise moment. So we have, that's going to be positive. So we have F, and the distance, the perpendicular distance is L1 times L1. And then we have FC here. Okay, FC is going to create a clockwise moment, which will be negative. So we have FC, and the distance, that the perpendicular distance there, is L2. And in terms of forces that create moments around A, we don't have any more. So with this, we can set those equal to 0. And then what we get out of this problem is FC is equal to, what is that equal to? L1 over L2 times F. Okay, so with this we see that the force of the clamping really depends on how hard we're clamping on the handle. In addition to that, the ratio between the links. So this is what we would get for a mechanical advantage, L1 over L2. All right, so that is the clamping force. In addition, we may want to find what the forces are on the pin here. And to do that, we can continue. Let's take the sum of the forces in the y direction and set those equal to 0. Now we have F here pointed downward. Oh, too far. So F, negative F. And then we have AY pointed upward. And then we have a component of FC. And actually that will be negative FC. And the component of that is, if this is theta here, this is theta, that's FC cosine theta equals 0. So solving this, we have AY is equal to F plus FC cosine theta. All right. Additionally, we can take the sum of the forces in the x direction and set those equal to 0. And there we have AX, and then we have plus FC, and this time it will be sine theta, will be the component in the x direction set to 0, and we have AX is then equal to negative FC sine theta. All right, so we've solved for the forces in the pin joint as well as the clamping force. Now, we didn't analyze the upper arm or the other part of the plier here, but we could, and we could solve these equations simultaneously. So let's just take a look at the other side of the plier here. So here is the other side, and likewise with the internal forces here, we need to make sure that our forces are canceling each other out as we add everything together. So FC has to be pointed this direction to make sure it cancels out this up here, and then AY, since AY is pointed upwards here, on this diagram, it must be pointed downwards here. So downward there. And then AX must be pointed to the left. So by using this method, if we were to add everything up again and assemble everything together, all of these would cancel out.